For our final video in this lesson, we're going to just work some sample problems dealing with the transformation rules. Now, some of these problems will look familiar from some of the work that we did in Unit 1, and that's fine. I just wanted to show you the more formal value of the rule itself and how this can actually apply to some of the other functions as well. So let's just take a look. Sample problem number 1. It actually wants us to graph the f of x equals absolute value of x, and then it wants us to graph the negative value or the negative version of the function. So g of x equals negative absolute value of x. Now notice that we're still plotting, if you will, points, and you can do that here if you wanted to do simply a t-chart. You know, we could do -1, 0, and 1, and you should at this point with the parent functions know what this graph is going to look like. So the absolute value of -1 is 1, 0, 0, and then the absolute value of 1 is also a positive 1. So we kind of get the start of our V shape going, and of course you would try to be a little bit more artistic than I am. Use straight edges to hit the correct points. So that's kind of a terrible looking absolute value function. But if we did the reverse effect of this, so if I did x and I did g of x, we're going to see that -1, 0, and 1 is going to give us the opposite effect, because after we take the positive value from the absolute value function, we're going to negate whatever comes out. And so that's going to give us -1, 0, and -1 for our y values. And so we're going to still be at 0, 0, but this time the v is actually of the absolute value has been reflected across the x-axis. And so it asks us to describe how they're related, and they're basically reflections of each other. And so assuming I actually drew the absolute value through the points that it's supposed to be going to, it would look more like a mirrored image of each other. So do this on your calculator to get a better view. I know sometimes sketching on a computer is not the easiest thing to do, so always use your calculator to give you a better sense of what's going on here. Alright, let's move on down to sample problem number 2. We've got an A and a B, and then of course on the next page we have parts C and D. So we'll focus on A and B first. Now, both of these are graphs that you should be familiar with. I just want to formalize the rule here. If we look at the square root of x plus 2, what this is basically doing is it's taking the function and then it's adding the c value outside of the function. And so that's going to create an upward shift of 2. So I'm going to go to 2, and then of course that's going to give me a few more points, and that means my square root is just going to start from 2 units higher than the origin, like the parent function did. And so that is the graph of square root of x plus 2. And again, always check these on your calculator. Now, for f of x equals x minus 2 squared, we actually subtracted the c value inside the function. And so this is one of those situations where the rule took place inside the function, and this is going to have an opposite value shift to the left or to the right. In this case, since it's subtracting 2, we're actually going to go 2 to the right before we start our upward shift here. And so our upward graph, quadratic, should look something similar like that. So we have a shift to the right 2 units before we start the upward facing quadratic. And so you can see the formalized rule and how it plays into each of the graphs. Now, the next one, the c value, is going to be a little different. Now, this is the greatest integer function. It's got this kind of double look in brackets, if you will. What the greatest integer function technically is what we call an infinite step function. So what happens here is that we have this step function that'll go on infinitely. Now, each part of the step function is 1 unit long horizontally. Now, what the 2 value does in front of it, it's the same effect of multiplying a value to the whole function, and it's greater than 1. So it's going to have this version of stretching it horizontally. and it's going to give us a little steeper look. Now, what that's going to do is, and I'm probably not going to be super detailed on this, but you can kind of get a sense. We're always going to start that 0, 0, unless we added something to the x value inside the greatest integer. So we're starting at the origin, but instead of taking a step 1 unit at a time, that multiple of 2 is actually going to have us taking a step 2 units at a time. Now, this is a little bit of a detailed graph, so it can be a little bit time consuming. And so I've got the top side of that, and then I've also got to do the back side of that. And this is kind of a tough thing to do on the computer because you can't see the open and the closed circles as well as you should be able to as you're graphing this, but you get a sense of what it's supposed to be doing, okay? And if you graph this on your calculator, you won't see the open and closed circles either, so you just have to understand that they're part of it to keep it being a function. Because if you think about this, if I did a vertical line test and I drew a vertical line straight through there, I have to have one open and one closed so that I don't have a repeating x value. That keeps its function rule. So, alright, and finally we're going to look at this final one. We actually have two things going on here. We have a value being added inside the function, and we have a value being subtracted outside the function. Now we've replaced these c's in a lot of cases with h's and k's, and that just kind of gives us a nice starting place, if you will, for the parent function. And so inside is going to be opposite, so I'm going to go -2 and a +1. And that's a really easy starting place for me to graph this cubic function. And so if you recall, the cubic function looks a little bit like this. And then, of course, kind of curve through here and just do the best you can to sketch that through the appropriate points. And so we had a shifting to the left and upwards for our parent function, but it still looks like a cubic. So, alright, those are some good examples of the transformation rules taking place over a number of these. We will work in more detail with the various new parent functions and the transformations in class. And I'm going to recommend that you play around on your calculator to get a better sense of these things. The more you mess around on your calculator with the various parent functions and the transformations, you'll have a good sense of what's going on. And as always, be sure to write down questions and ask them in class.